Hey guys, welcome to video 54. Today we're going to do a small signal analysis of the collector feedback biased common emitter amplifier. We looked at this circuit way back in video 19, and at that time we weren't quite ready to do a full-blown small signal AC analysis, so we just derived the biasing equations. The circuit is shown here and the equations we derived are over here. We're going to make the usual transistor approximations today. That is, alpha is approximately equal to 1 and beta plus 1 is approximately equal to beta. The circuit we're going to be working with is shown over here. We have the input signal capacitively coupled to the base and the load capacitively coupled to the collector. All right, we're going to start out with a derivation of the input resistance of this circuit. And something I've noticed in all the textbooks and references that I could find and the presentations online, nobody really gives a fully detailed analysis of this circuit under small signal conditions. And I kind of think that does a disservice to the readers and viewers, so we're going to correct that today, and let's go on over to the next page and start our analysis. Alright, so here we've got the small signal representation for the amplifier, and in this one I've used the pi model for the transistor. Normally I'd use the R or T model as shown here, but I thought I'd use the pi model for a change. It's just the equivalent of this circuit where we move little re over to the left and show it as beta times little re. Sometimes that's called R sub pi. And you can see why it's called the pi model, because it's kind of shaped like the Greek letter pi. All right, well, coming back to our circuit here, the first thing I'm going to do is KVL clockwise around this outer loop, and that's going to give me 0 equals V in minus I sub F times RF minus V out. And of course, V out is equal to negative I sub O times R prime C. So that's V in minus I sub F times RF plus I sub O times R prime C. All right, now I'm going to do a little bit of Kirchhoff's current law at node C here. And the most obvious thing that strikes me is that beta times IB is equal to I sub F plus I sub O. Now what I'm really after here is the equation for I sub O. So let me solve this, and we get I sub O equals beta times IB minus I sub F. Okay, and we're going to substitute this back into this equation we derived up here for using KVL, and what we get is 0 equals V in minus IF times RF plus R prime C times beta, so beta R prime C times IB minus I sub F times R prime C. Okay, let's stop here for a second and catch our breath and take a look at this equation. What we've got is one equation in two unknowns. The unknowns are I sub F and I sub B. All right, but if we come over and look at the circuit, notice that IB is equal to V in over beta times little re. So we can make that substitution into our equation and reduce this to an equation with one unknown. So let's go ahead and do that. So we end up with V in minus I sub F times RF plus beta times R prime C times V in divided by beta times little re minus I sub F times R prime C. The betas cancel, and we can write this as 0 equals V in minus I sub F times RF plus V in times R prime C over little re minus I sub F times R prime C. Now what I'm going to do next is move these V in terms over to the left hand side of the equation, and that's going to give us V in plus Vn times r prime c over little re equals I sub f times rf plus I sub f times r prime c. Next thing I want to do is factor Vn out of both of these terms and I sub f out of these. And if I come up here, that's going to give me Vn times 1 plus r prime c over little re equals I sub f times rf plus r prime c. All right, now let's go look at our circuit here for a second. Note that Vn driving the feedback resistor produces IF, so the input resistance looking into RF is Vn over IF. We can solve this equation for Vn over IF and we'll get the input resistance to the feedback resistor. So let's just go ahead and do that, right? We'll call that Rin to the feedback resistor, and I'll put a prime there because I'm going to use this notation again later. So R prime in to the feedback resistor is equal to Vn divided by I sub f, and that's going to give us Rf plus R prime c divided by 1 plus R prime c over little re. And notice R prime c over little re is just the gain of the amplifier without any feedback resistors or anything. That's just the normal voltage gain. So we can rewrite this as R prime in to the feedback resistor is equal to Rf plus R prime c divided by 1 plus the gain magnitude. And what can we do next? Well, in a normal circuit, RF is very large compared to R prime C. Typically, RF is around 100,000 ohms or more, and R prime C is usually in the range of thousands of ohms. So very often we can ignore the R prime C term up here and say that R prime in looking into the feedback resistor from the Vn source is approximately equal to Rf divided by 1 plus the gain magnitude AV. All right, now we're almost there. What we need to do next is factor in beta times Re into our input resistance equation, because Vn is looking at beta Re in parallel with the resistance looking into RF. So what we end up with is our overall input resistance with feedback, Rin with feedback, Rinf, is equal to beta times little re in parallel with Rf plus R prime C divided by 1 plus the open loop gain magnitude. Sometimes we call AV with no feedback the open loop gain A sub OL. Okay, that means open loop, open feedback loop gain. Okay, and sometimes you'll see this 1 plus AOL. But anyway, there is our input resistance equation for this circuit. And of course, you know, I'm going to have a nicer version for you because I love you guys so much and I don't want you to suffer through this terrible writing. So here it comes. And there you go. Okay, now the next thing I want to do is derive the voltage gain for the circuit. So let's go on over to the next page where we've got a clean slate. And I'm going to do a little preliminary work here based on KCL to start with. Remember, at node C, beta times IB is equal to I sub F plus I sub O. And if I solve this for I sub F, we get I sub F equals beta times IB minus I sub O. Now, remember, the base current is equal to Vn over beta times Re, so we'll make that substitution here. I sub F equals beta times Vn divided by beta times little re minus I sub O. And the betas cancel, so our feedback current I sub F is equal to Vn over little re minus I sub O. All right, now I'm going to use some work from our previous derivation to save some steps here. And in particular, on the previous page, we have the following KVL equation. 0 equals Vn minus I sub F times Rf plus Vn times R prime C over little re minus I sub F times R prime C. Now we're going to substitute in this identity for I sub F, and that gives us 0 equals Vn minus Vn over little re minus I out times Rf plus Vn times R prime C over little re minus Vn over little re minus I sub O times R prime C. Now what we want to do next is distribute Rf through this factor and R prime C through this one, and that's going to give us Vn minus Vn times Rf over little re. Here we're going to end up with a plus sign, so we're going to get plus Rf times I sub O plus Vn times R prime C over little re minus Vn times R prime C over little re plus I sub O times R prime C. And notice these two terms are going to cancel out, and that leaves us Vn minus Vn times Rf over little re plus Rf times I sub O. Let's see, plus, let's move R prime C over and do it R prime C times I sub O. All right, now what I think I'll do next is move these terms that contain Vn to the left-hand side. So that gives me negative Vn plus Vn times Rf over little re equals Rf times I sub O plus R prime C times I sub O. And if we factor Vn from the left side or I sub O from the right side, we're going to get, well, let's see, Vn times Rf over little re minus 1 equals I sub O times Rf plus R prime C. And we're going to solve this for I sub O. That means I'll just divide both sides by Rf plus R prime C. And that gives us I sub O equals Vn times Rf over little re minus 1 divided by Rf plus R prime C. Okay, we're getting a little bit cluttered here, so again, I'm going to clean things up a bit and make some room, and I'm going to carry this equation up here and start with it. And remember, that's our equation for I sub O. All right, now I'm going to clear some fractions here because this is a compound fraction mess. So let's see, starting here, we've got Vn times, we can convert this into Rf over little re minus little re over little re to get a common denominator. So we get Rf minus little re over little re divided by Rf, well, R prime C plus Rf. Right. And now let's multiplied by the reciprocal here, and that gives us I sub O equals V in times RF minus little re divided by little re times 1 over R prime C plus RF, and that gives us V in times RF minus little re divided by little re times R prime C plus RF. Okay, now looking at the circuit, remember V out equals negative IO times R prime C. So we're going to end up with here V out equals negative V in times R prime C times RF minus little re divided by little re times R prime C plus RF. Okay, now we're really close to the end here. Remember, the voltage gain is V out over V in, so V out over V in is AV, and let's call it AV with feedback, and that's equal to negative R prime C over little re times RF minus little re divided by R prime C plus RF. All right, so we can think of this as our open loop voltage gain, that is the gain with no feedback at all, and this is a correction term that we scale this by when we have this feedback resistor present. So AV with feedback is equal to AV without feedback times RF minus little re divided by R prime C plus RF. Now, as a practical matter, little re is usually maybe 10 ohms or so, and RF is 100,000 ohms. So we can approximate this as AV times RF over R prime C plus RF. And a lot of times R prime C is negligible compared to RF, so our correction factor turns out to be really close to 1. So our actual voltage gain with feedback is going to be slightly less than the open loop voltage gain. And if you want to be really accurate, you can use this version of the formula, but this one is probably going to be the one that's most useful. Now, as always, I've got a nice version of this derivation for you, so let me paste that in here. And there you go. You've got something worthy of a screen capture. Okay, now the next logical step is for us to derive the output resistance of the amplifier, but before we do that, I want to try and read your minds and answer a couple of questions you might have right now. Number one, what would happen if we derived the analysis equations with no load on the amplifier? That is, with RL equals infinity. Well, all we would do then is replace R prime C with RC, just the collector resistor itself. And question number two, what would happen if we derived our equations using R sub pi equals beta plus 1 times little re instead of the approximate value R sub pi equals beta times little re? Well, in that case, mainly what we would end up with is multiplying the gain terms, or sometimes R prime C in our equations, by the alpha of the transistor. That is, alpha equals beta over beta plus 1. And those modifications are shown here in the green boxed equations. Going through the derivation with R sub pi equals beta plus 1 times little re gives us these versions of the equations. All right, now let's go on over and derive the output resistance. So fasten your seat belts again, and here we go. Notice I've removed the smiley face and replaced it with a grimace because this algebra can be pretty daunting. But going on down to the next slide, we're going to determine the output resistance using Thevenin's theorem, and we'll use the short circuit method. Another thing to notice here is that I'm using the accurate model for the transistor where we're using beta plus 1 times little re to represent the resistance looking into the base of the transistor. All right, first thing to do is remove the load resistor and determine the open circuit output voltage V sub OC. That's pretty easy to do here. It's just going to equal Vin times the voltage gain, and we previously derived the voltage gain. So we've got two different versions of it here. We can use whichever one is more convenient. The next thing we want to do is determine the short circuit output current. So we place a short from the collector to ground. That removes RC from the circuit, giving us this equivalent. And a couple of things we notice right off the bat is that the base current is equal to Vin over beta plus 1 times little re. That is, I sub B equals Vin divided by beta plus 1 times little re. And also, since we grounded our collector, the feedback current I sub F is simply Vin over RF. That is, I sub F equals Vin divided by RF. Now going back to our circuit, we're going to do a little bit of KCL at the collector, and we find that I sub SC, the short circuit current, is equal to IF minus beta times IB. Now what we're going to do next is substitute these two equations into the I sub SC equation, and that gives us I sub SC equals Vin divided by RF, that is the equation for IF, minus beta times IB, so we're going to have beta times this, that's beta Vin divided by beta plus 1 times little re. And notice we could factor this out and call it alpha if we want to, and that would give us Vin over RF minus alpha times Vin over little re. And if we factor Vin out of this equation, we get I sub SC equals Vin times 1 over RF minus alpha over little re. Okay, now to save myself a little bit of messing around in the next step, what I want to do now is put these two fractions over a common denominator. So that's going to give me I sub SC equals Vin times, let's see, little re over RF times little re minus alpha times RF over RF times little re, which is finally Vin times little re minus alpha times RF over R sub F times little re. All right, now what we're going to do next is divide V sub OC by I sub SC to get our output resistance. So let me clear off the workspace here, and I will carry my equation here to the top for I sub SC. Right, and let's make note of that so I don't forget. I sub SC equals this. So our output resistance then is equal to Vin times alpha and the rest of this. But notice we're going to be dividing the Vin out. So I'm just going to drop Vin at this point, and we've got R out equals alpha times negative RC over little re times RF minus little re divided by RF plus RC. This whole thing divided by little re minus alpha times RF over RF times little re. And we're going to multiply by the reciprocal of this denominator, so we get R out equals alpha times negative RC over little re times RF minus little re over RF RF plus RC times RF times little re divided by little re minus alpha times RF. Whew, boy. Okay, now let's take all these pieces and put them together and make something hopefully a little bit nicer. So we've got RO equals, let's do negative alpha times RC, and I'll bring this factor over, times RF times little re times this middle term, and that's going to be RF minus little re. And this whole thing is divided by little re times RF plus RC times little re minus alpha times RF. All right, and we're going to cancel out these two little re's. And let me clear the decks and we'll write our final equation here. Alrighty, let's get rid of this, and what we finally ended up with is R out, and let's put an F on here because it's including the feedback resistor, so we'll call it ROF is equal to negative alpha times RC times RF times the quantity RF minus little re divided by the quantity R sub F plus R sub C times little re minus alpha times RF. And you could factor AV out of this somewhere as well, but I'm going to leave it in this form. And finally, I'm going to bring up a nice version of this for you guys, because I know this was a really tough one. I've said this many times before, but this time I really mean it. This was tough, but here is the nicer version of this derivation. All right, there you go. Okay, let's go on over and summarize the results of today's trip into the circuit analysis meat grinder. Here's our circuit, and around it I have listed the most accurate versions of the equations derived today. This is the input resistance with feedback, output resistance with feedback, and voltage gain with feedback. Remember, for a typical transistor, you're going to be able to make a lot of simplifying approximations to these expressions, but as it sits, these are extremely general, and you can use them for this circuit with a transistor of any beta. All right, now what I was planning to do was apply these equations in some practical examples, but to be honest, I think this video is already too long and I've exhausted my circuit analysis energy for the day. You probably have too, so we'll save that for the next video, and I'll see you then.